Yeah. Okay, yeah, let's continue the lecture series by Chakrabarti. Okay, thank you. Recording.
Okay, so let's start. So far we have been discussing at the level of formalisms, and last time we saw specifically this sense formalism being used in the context of type-2 programming. And so today we are going to use that essentially type-2 programming sense formalism in two concrete instances, physics problems where they can be applied. So the first of them is very simple and sort of well known. It's essentially has to do with the fact that type-2A string theory is equal to type-2B string theory. This is something that is, among all the string dualities, perhaps the most well-established one that you can derive at the level of worldsheet exactly and so on and so forth. But in principle, this also means that there is a duality at the level of just the supergravity. And in particular, if I do a dimensional reduction of both of them on S1, I get some 90 theory here. Do a dimensional reduction on S1, I get a different 90 theory here, and these two 90 theories are supposed to be related to each other. Right? And the relation is, roughly speaking, if this one is being compactified on a circle of radius r, that is being over 1 over r, but essentially that means that there is some field redefinition which takes you from this one to that one. Right? So this is the sort of textbook story. And of course, there is a slight caveat in the textbook story when it comes to the discussion of this duality at the level of Subra itself. If you're dealing with the string level, you can of course bypass all of this discussion and just look at the vertex operators and how they transform the T duality, and you're done. And it's something that you can easily find in, say, Cochise. But at the supergravity level, there is a small subtlety, and the subtlety essentially has to do with the fact that this sector, this operation is kind of not a very well defined one. Simply because in the textbook you don't really have a well-defined action for the full type-2B sector. What you have instead is a pseudo action. So at some point, to make this connection, you need to do something by hand, right? So alternatively, if somebody sometimes comes and claims that I have given you a proper action for type-2B supergravity, then you should be able to do this computation just from first principle without introducing anything by hand whatsoever. So that's the claim that we are going to verify within sense formalism. But let's just quickly recap the textbook argument or the textbook story. How does this is sort of realized in this? And just to keep the story simple, let's look at the simplest case of conservative reduction, where I take the 10-dimensional metric to be so the x9 direction, the 9 spatial direction is a circle of something.
What does G subscript D mean about?
It's not
About
90.
Oh, it's 90. Oh, it's a 90.
It's a 9. Okay. Yeah, my 9 looks like a bit like G as well.
Okay.
Can you tell me if I like this? Or does it make worse?
No, that's nice.
That's nice? Okay.
That's right.
Okay. But by default, my 9 looks like this. So if I write 9, which looks like G, please, if there's a confusion, correct me. Okay. So the 9-dimensional metric is essentially, I'm going to, or the 10-dimensional metric, I'm going to decompose into a 9-dimensional Minkowski, and the x9 direction I'm thinking of as a circle. And the way I have parameterized it is that this R is dimensionless. This L is period dimension full, and the physical size of the circle, the perimeter, is R times L. Okay, so what essentially means is that it will essentially allow us to think of taking a dimensionless numbers going to zero limit as we shrink it. Because if it's dimension full, then taking to zero limit, what does it even mean? So you have to parameterize it in some terms of some dimensionless quantity, and that's this R that is sitting in the middle. And the x0 up till x8, this is the standard Minkowski space in 9 space time dimension. Okay, so this is not the most general KK reduction, of course, right? This is the simplest thing. You don't have anything happening in the Kalman field, and the transverse direction is completely flat. But this is enough to illustrate the thing that we are discussing. Just for pedagogy and simplicity, let's just focus on that. And also, let's only focus on the problematic piece, which is the kinetic term for the Raman-5 form. Because every other term that appears in the action, the dimensional reduction is not really a problematic issue. Everything else is a well-defined term in the action by itself. It is only this guy in the type 2D action which was problematic. Right? So, for the purposes of this discussion, it is enough to just focus on this with this case, just to see how the whole thing works out. And of course, since we are in textbook, our F5 is given as a field strength of a Raman potential, which we usually call C4. And then essentially, what you do is that since the 9th spatial direction is a circle, the statement is you just mode expand. So you have to mode expand this C4. So just Fourier expansion in the 9th direction. This is the standard Fourier phase that you would have if there's a circle in the x9 direction. And on the right hand side, implicitly everything is to be now thought of as a function of only x0 till x8. The x9 dependence is purely in this. Right? This is just simply using the fact that it's a function in a periodic space, and I'm just using Fourier decomposition. Right? And the 4 form would naturally decompose into something which is a 4 form in the lower, in the 9-dimensional space-time, and a 3 form in the lower 9-dimensional space-time. Right? Everyone has seen some version of this before. So and I'm not going to write the dependence on the right hand side on the x0 till x8 explicitly, but every time I work in the lower dimensional quantities, it should be implicit that things only depend on space-time on that. Okay. And then essentially, you plug this whole thing in here, DC4 weight star G DC4. This whole loop expansion, it gives an infinite number of terms. But then if you take the limit of shrinking limit of the circle, then the only mode that essentially contributes has to be the 0. Right? Because it only this C4 never enters by itself, it always enters through B of C4. A derivative is always going to pull out a factor of this N, which is going to give masses to all the hard modes. So it's only the massless mode that is going to contribute. So essentially, it's only the 0 mode that is going to survive in the dimensional reduction in the 90 action, right? So in changing limit of the circle, substitute interaction, and this is effectively means keep plus the 0. And so for the 0 mode, I'm just going to drop the subscript C0 because it's meaningless, because only the 90 effective action, those are the only ones which appear. So essentially, this action, the dimensional reduction, goes to some 9-dimensional action, which is going to, this is now an integral over 9D. So effectively, it boils down to two terms. One is a wedge product of the field strength of C for which this C4 is the potential, and one is a 4-dimensional field strength for which the C3 is the potential.
Sounds explosive.
So this is the end of the computation. But then this is the what you get from the type 2B story. If you do the similar thing from the type 2A story, of course, type 2A has all the other fields. The thing which is supposed to match with the type 2B story is where you start off with the Raman 4-form field strength, right? And the 4-form field strength, when you do dimensional reduction, it's going to give you a 4-form, and then it's going to give rise to a 3-form. The 3-form is something that is going to match with the 3-form from the type 2B side. So you do forget about that. In the type 2B side, so type 2A side, it's supposed to match with a single kinetic term of a 4-form potential. So here you have something which is extra. So definitely you're not going to get a 5-form starting from a type 2. But in 9 dimensions, 5-form is nothing special. You can always kind of dualize it and trade in for this 5-form for a different 4-form.
I have a question. So, what is the Hodge dual with respect to?
This is with respect to eta.
Okay.
So I'm still following the convention. If I don't give a subscript to the Hodge dual, it's always with respect to flat.
Okay.
But of course, I mean, here if you had started off with something else, it would have been that Hodge dual, but then that would have also introduced some other factors in it. It's the simplest thing. So here we have a situation. So you have basically two for sort of field strengths, and on the type 2A side, S9 2A, you're supposed to get only something like F4 with star F4, where F4 is some DC tilde 3. So if this is supposed to match with this, we have to somehow find a way to get the read of one of these guys, right? So one nice step that you can do is that so what you do at this point, you can say that in 9D, you can always trade off this F5 in favor of some H tilde 4 by using, so this is essentially what we call H pointer rule. Right? You introduce a total derivative, which is like F5 wedge H4. And H4 you also think, this H tilde 4 you think of as a field strength of some DC tilde 3. And you integrate out the F tilde, and in favor of, you get a quadratic action of H tildes. So the problem that there is a 5-form is not a serious problem, because a 5-form in 9 dimension, you can always think of it like as also as a 4-form. in 9 dimensions. That's okay. But now you have a more serious problem, which is like you have two 4 forms. Right? Whereas in type 2, you would expect only one 4 form. So what's the issue? And at this point, the textbook reminds you that this original, all this H. So basically now your S9 looks like H tilde 4, H tilde 4 plus 4, H4. So at this point, your textbook reminds you that the 10-dimensional parent field, this was supposed to be self-dual, and its consequence in 9 dimension would essentially tell you that these two are essentially related. So they are not really independent. You're supposed to only work with one of them. And that's the resolution of the conundrum. So it's okay to drop one of them and keep any one you like. And then correspondingly, you find the field definition which matches you with the thing that you get from the type theorem. Now, there is, of course, one thing, there are two things which are quite dissatisfactory about this. One is that the simplest thing that I've been saying for a few weeks now is that you need to introduce this by hand. But what is more problematic to me is that even within the pseudo actions flow of logic, this is kind of inconsistent. Because remember, this self-duality condition within the pseudo action formalism is supposed to be something imposed only on shell. But here you are kind of demanding it off shell as well, because this is a statement at the level of the actions. Right? I'm not deriving this for some equations of motions and everything. I'm really just taking an action and I'm just doing a dimensional reduction.
So could you just repeat the argument again? So you're starting in M, you have this self-dual guy.
Yeah.
And then you take the self-dual guy,
So this is not yet self-dual. So this is the textbook formalism.
Right.
This is just an ordinary 5 form. I do dimensional reduction. Yeah. I get a 4 and a 3 form, and effectively its action is like a 5 form field strength and a 4 form field strength. I dualize the 5 form field strength in favor of another 4 form field strength. So I can have an action which has 2 4 form field strengths. And then at this point, by hand, I demand that, okay, the original one was supposed to be self-dual. And I kind of ignore the fact that, if this was self-dual, then that would have been 0. And what does it even mean to do dimensional reduction of something 0? But we just say that, okay, if this was really self-dual, then it would really mean that this F5 and H4s would be dual to each other, which means that this H tildes and H would have some relation among themselves.
So, but instead of dropping it, wouldn't you just add them up and get a factor of 2?
Yeah, I mean, if you do it consistently, then you would actually get 0 because they would just cancel, right?
Or they have the figure.
Yeah, exactly. But I mean, at this point, what people do is that it's not a very sort of, as I'm saying, that this is not a very consistent step. This is not a very logical step. What textbooks do is that at this point, they say that you are really not supposed to get 2 copies because if you had started off with these, you are supposed to get only 1 copies and blah, blah, blah.
Yeah.
And then they just drop it by hand. Or drop any one of them. And then that matches, which is, of course, the best you can do because, frankly speaking, you don't really have an action for that. So your dimensional reduction is reducing something that is completely different. It's not supposed to match with that.
There's a follow-up question. So if you take the iron nodes, they're massive. So the C3 combines with the C4 to make a massive C4 in some sense. The massive form field has more degrees of freedom than the massless one.
Yeah.
You need a C3 to make up the full massive form. So that story should work also somehow.
Yeah, it should, but in this case, it really shouldn't, in the sense that because the dimensional reduction of an ordinary 5 form and a self-dual 5 form are supposed to be very different. So here the whole problem is coming is because we are dimensionally reducing an ordinary 5 form. And then at some point towards the end of the calculation, just by hand throwing something off, which I cannot justify by any means of logic. And it's really by hand just throwing something off. Simply because I know the answer that I'm trying to get to. If I, for example, if I didn't know type 2A, there is no reason for me to just going beyond this line. This line is fine. You can get this. But then after this, throwing away any one of them, it's a completely by hand thing. And what I'm saying is that it's not even consistent with the internal logic of the pseudo action formulas, where you're supposed to demand this at the space of solutions, not at the level of action itself.
Are you saying that we are throwing away in this ad hoc fashion?
One of them, any one of them. Any one.
Are they completely equivalent?
I mean, in a sense that this is, you need one of these guys to match with the type 2 answer.
Ah, okay, that's because we don't know which it should be.
Yeah, a priori you don't know, right?
Yeah.
Right, but then these people are saying that, okay, I mean, this is kind of equivalent. Like whatever degrees of freedom is encoded here is the same degrees of freedom encoded here. So you throw away any one of them.
Yeah, I'm very tempted to go the other way of saying that, okay, if I have a 4 form in type 2A, then more than speaking, that should be viewed as 2 self-dual 4 forms. Degree of freedom.
Self-dual in what? Because in 9 dimensions you can't have a self-dual series. The type 2A side is sort of completely non-controversial, right? We have a well-defined action in 10D, we do a well-defined computation, and we get this. This is completely non-controversial. It's only the 10D side which is controversial for type 2B. And then, of course,
Okay, so the self-dual in 4 form, if you type to be, that is a derived notion from the 5 form.
Yeah, exactly. Right, so I mean, this is at this point you buy and throw away H tilde or H and keep one, keep the other. And then you say that, okay, fine, you can find a field redefinition that gives you a map with the type 2A. And this is where the textbook kind of stops. And then, of course, I mean, this is not very surprising because if you don't have a well-defined action on the type 2B side, of course, this is sort of very iffy, not at all consistent or rigorous step, but somehow it matches, so we don't care.
But at the equation level, it should be like much.
Equation for motion level is fine.
Yeah.
Equation for motion, you can do a dimensional reduction on the type 2B side and type 2A side, they match completely fine. Yeah, so that is true. So this on this top, this diagram that I draw, this is something that is definitely true at the level of equations. But I mean, we know this to be true at a much higher level, right? This is something that you can prove at the full string level, including all the massive modes and so on and so forth. This is one of the most well-established duality symmetry in string theory. It's not conjecture, right? It's something that you know. At the perturbation level, you know that this is an exact duality.
And the same argument goes through in any 4.5 dimensions.
Well, I don't know if any arbitrary 4+2 dimensional, there will be a equality kind of relationship, right? But dimensional reduction, yes, I mean, of course.
The dimension we're talking about.
Yeah, dimensional reduction, of course. So whatever we discuss here, you can easily replace this to work within any 4+2 dimension on a circle. Yeah. Okay, so then the philosophy is that if we start with the same type of reaction that we wrote down last time, right? Then we shouldn't have to do any iffy steps. We should, this side of the story is also sort of consistent. We do a dimensional reduction, and we should see that it matches with the type 2 I mean, okay, we have to find the field definition, but I mean, it should match. And there's no further extra input that is required at any point. So it should be a pretty simple computation, and it is a pretty simple computation, but it's still both doing it for a couple of reasons, because there are a couple of questions a priori which are not completely clear. And I think it's related to what Stephen was asking towards the end of last lecture. So one is that so first and foremost, the statement is that you remember that this sense formalism, the fundamental degrees of freedom is like a field strength line variable. It was not a potential. The fundamental thing was really like the R5 form flux, right? And why is that interesting? Because if you look at the mode expansion, right, you were supposed to do a mode expansion of the fundamental field itself, and then everything else follows from as a consequence. We did not mode expand F5 there. We mode expanded C4, and F5's mode expansion follows from the fact that it's D of C4. So if you do a mode expansion of C4, then it's forced on you how the mode expansion of F5 is supposed to look like. In particular, it meant that that mode expansion is always going to pull out a factor from the exponent which is proportional to the higher modes. If you do a direct mode expansion of the field strength, that is not going to be true. So in principle, this suppression of these higher modes is not naively obvious. It's going to happen in sense formalism. Is this clear? If I have a scalar phi and I mode expand this, in terms of this and etc., and then I have an action in terms which is solely expressible in terms of del phi's, then this guy is always going to be like proportional to in times in, etc. And any quadratics of del phi's would have a quadratic of n square, which is basically giving it the mass, the conservable power. So everything except for the zero mode is massive. And the mass is precisely something which becomes infinitely massive at the limit of shrinking circle, which means that they decouple. But now I'm saying that we have something which is equivalent of del phi, but it in itself is a vector field, like any. And if I mode expand this guy, I will get something like a small mu in exponential. And then if I have a quadratic of these guys, mu, then there is no reason for me to drop all the hard nodes. I'm just getting an infinite number of quadratics. So this is quite subtle. The moment you trade off your potential with a field strength like this, you have to answer this question that what happens to the higher nodes? Because in supergravity, you don't see the massive nodes making an appearance. The culture line covered completely is supposed to be covered. It's only the massless zero modes which are supposed to be true at the supergravity level. So it would be interesting to see how that happens. Of course, it has to happen, right? Otherwise, it's already reached. And the second is that, as I keep on saying, that the coupling to gravity is non-standard. So this will actually allow us a sort of small example to compute M explicitly. And the third point is also quite interesting because it's related to the first point actually. This one is a field strength based formulation. We are trying to make connection to the type 2A, which is a potential based formulation in the textbook formula. So we have to somehow figure out at some point of the computation how to go from field strength to the potential based formulation in a very natural way, not by doing anything which doesn't make rigorous sense. So make connection to potential based formulation of factory also.
And what symbol is in the quotation mark? Is that an N or U or is this the manifold?
No, this M is the gravitational coupling. Remember, in Ashoke formalism, we wrote
the big M matrix.
the big M.
Yeah.
So even though this computation is very simple and I have made it even simpler working in the simplest setting, there are still some subtle conceptual issues which one has to resolve. And of course, we will see how they get resolved. The computation, I mean, in this sort of thing, the computation actually is very straightforward. There's nothing fancy going on. But it's kind of interesting how this sort of points gets addressed along the way. That's the interesting part of this computation. Oh, I think I didn't mention the reference. So this is this paper that I and one of my collaborators wrote last year. Or rather, just the first section of that paper. Okay. So the first thing is, let's try to calculate this M. So once again, just to remind you that since we are only focused on the kinetic piece, in the full type 2B action that we wrote down last time, you can forget about everything else, and it's enough to focus on just the one which is the cell dual thing, which was, to remind you again, I hope I have not changed the conventions again, but okay. So this is the thing which is analog to the F5 with star G F5 in the situation as we discussed. Right. Of course, you needed the extra field to give dynamics to Q, and you needed this so that Q knows about the gravitational coupling. Okay. So the first, let's first compute this M, because as we discussed, once somebody has given me what is the space-time metric, that is enough data for me to explicitly figure out what this M is. Right. So compute M. So it has been a couple of lectures since I told you how to the general prescription for this M. So the basic thing is that first you construct a basis of eta self and anti-self dual forms. And this index uppercase I, j is, this will run from 1 to upper 10 to square. So these are the indices, the dimension of vector spaces of self dual and anti-self dual forms in 10 dimensions. So the first step was to construct a basis of eta anti-self dual and eta self dual forms. The plus minus are self dual and anti-self dual.
In 2 dimensions, it would be like Zweibines with Lycombe coordinates or something like that.
Yeah, they would precisely be the Lycombe coordinates because it with respect to eta.
Right, the Lycombe coordinates with respect to eta.
Exactly. And so we are going to construct them in 10 dimensions also. So just to remind you that what was the prescription. And then you also needed to construct a basis of G self-dual forms. And then I said that locally you can always express these bases lambda i's in terms of some matrices multiplying lambda, small lambda minus and small lambda plus. And once you find these matrices curl E A and curl E S, this matrix in matrix notation, the same was given as S inverse A up to negative sign. That was the construction that I proved. I told you it was kind of like I gave you a set of properties that A must satisfy. And then we showed that if you construct M like this, it satisfies all the properties, and with that, it has all the nice features and so on and so forth. So this is the algorithm that we are going to follow now and figure out M.
What is the, oh, okay, so it's a, what, an A or? what?
It's a curly A.
Okay, curly A matrix, okay.
This is the moment in which.
Oh, I guess it's.
And this is the one inside here.
Yeah, exactly.
Okay. Right, right. Yeah, I need to sit down at some point and just calculate this to see what it looks like for some explicit.
Yeah, we will explicitly evaluate this now. I just reminded you that what was the prescription. Now we're going to construct this lambda, small lambdas, this capital lambdas. Then once we have constructed this, we can always find the linear transformation which takes one from the other. That will determine these matrices. Once you have these matrices, you have this. Okay. Okay. So a natural choice for the lowercase lambdas is simply if somebody gives me a basis of 4 forms in the Minkowski space, which is the thing that will remain after we do the dimensional reduction in the 9-dimensional Minkowski space. And in terms of that, it's simply to just take this 4 form, wedge product it with Vx line, and just take its self-dual or anti-self-dual combination depending on whether you want to construct lambda plus or lambda. That's the simplest thing. Right? So gamma is, for example, gamma is like dx0 up to dx3, or it could be dx1, dx4, you know, all these combinations. Right? I don't want to write 5 dx's all together. It's a shorthand notation.
Is it just coincidence that you call them gamma?
I don't know. I mean, we didn't think much about why we call them gamma. It was system notation.
I thought gamma matrices, yeah.
No, nothing like that. It was, I don't know why we called it gamma. So it was just something that popped up at that point, and my collaborators didn't object, so it's still. No, but it has nothing to do with gamma matrices. This is really what I have in mind.
Okay.
Like this.
Okay.
So it's a set of nice orthonormal bases in the law 4 forms in the 9-dimensional ecosystems. No,
But still, it's closely related.
it's closely related, but okay. I mean,
It's not a bad choice.
it's not a bad choice. Okay, thank you. My subconscious might be thinking that, but I did not consciously think of it. So this is a very natural choice, right? And then a natural choice for the uppercase lambda is do the same thing, except now you this one, that's not. You do a Hodge dual with respect to the G, because you want this guy to be self-dual with respect to the actual metric.
So essentially you can choose anything instead of gamma wedge dx9.
Yeah, I mean, in principle, as long as it's a basis, it's fine. But I'm just saying that this is the simplest basis that you can think of, right? I mean, if somebody has given me a coordinate chart, this is really the most natural basis of cell-dual and anti-cell-dual formulas that I would construct. And most of the time they would suffice, right? Unless we have some sort of weird geometry going on.
So in 2 dimensions, this would be very simple.
Yeah,
In 2 dimensions, it would be very simple.
in 2 dimensions it would be very simple, but even in these dimensions it's very simple, right? Because you really don't need to know what commas are. That information. In fact, as I should point out that okay, I mean, I'm doing this explicitly for 10, but I mean this 10 is sort of nothing special. You could have just easily replaced this to be the 4n plus 2f direction in some 4n plus 2 dimensional manifold, and these lines would now run over the different values, and this is for h1 simplest h1 reduction in any thing. But of course, we are going to do it in the context of type 2B supergravity because there is a nice physics aspect where we get the connection. But the computation of n is basically the same for h1 reduction on any other. Here.
So I mean, in 2 dimensions, you could start with dx1.
dx0 or dx1.
And do this, and so you get from the first line, you get like, if you're taking a face value, if you start with dx1, you get dx0.
Exactly.
Plus minus, and you get
Exactly.
stuff.
So this one would be exactly dx0 plus minus dx1. That's it. And then this would be dx0 plus minus star g of dx0, which would be proportional to dx1, but depending upon what the metric is, it could have some radius factors sitting in front of it and stuff like that.
But is there, I mean, the whole sort of formalism doesn't really care how you choose the
No, it
small
doesn't.
lambdas. Right?
Yeah, it doesn't. As long as this forms an autonomous, the only thing we use is that this guy forms an autonomous basis, because we use the autonomality condition in simplifying one of them. And for these guys, we only needed them to be a basis. I don't even need to introduce the minus for this guys. Because eventually my theory is only sort of aware of the cell-dual combination.
But if you choose the thing you start with, I mean, I guess there are ways of choosing it so that even the small lambdas has some more properties than just being eta self-dual or anti-self-dual, in the sense of, being diffeomorphism or covariant.
You can, but I would say that it will never be diffeomorphism invariant because this forms a basis for the ether forms.
Yeah.
And they are never supposed to transform nicely under the diffeomorphism of the manifold in the metric G.
Do you care if they transform nicely or not?
No, I don't, of course.
So they could. In principle, they could.
But I don't think they would, because this guy transforms nicely. This one would transform nicely, but this one. So the linear combination would never have a nice one.
So I'm thinking, to me it sounds like you would want to choose them to be the Zweibeiners. Like having them to be the eta to be the metric in the tangent space.
Yeah, that's essentially it. Except that then I'm going to lift this and make it true. So I'm going to. So this one, if you think of in terms of this field lines, then this one will use field lines where the physical metric is also eta. So it's really the trivial sort of field lines. It's a one where this E will also be eta. But here I choose field lines E hat, which will be the metric G. So if
in the way you chose it now. But you could possibly choose the first guys so that the EE doesn't become eta but is G. Could you? Or not?
I can only make this with respect to G if I change this one to star. and I don't want to do that.
I guess you're sort of insisting on doing the duality in the coordinate. The Hodge operation on the coordinate indices, right? So,
Yeah, the Hodge operation is of course dependent on what metric I'm choosing. This Hodge operation is definitely Hodge operation with respect to the flat mean cosine metric.
right, but you could write.
You want to use flat indices,
Right.
but it is
Right, but like, I guess, then you're doing a Hodge operation on the flat indices with a flat epsilon tensor. But that's not what you want to do. Your star does not do the Hodge operation on the flat indices, it does it on the curved indices.
Yeah.
So that's where my vision
Yeah.
goes wrong sometimes.
Yeah, so I mean, in the sense that you can still use your vision, there's nothing special about using these coordinates. You can easily do everything in tangent space indices. All I'm saying is that in here, I would express everything in terms of real lines, which would have this property, which would really not be the sort of the physical real line, so to speak. On here, I would use real lines, which would have this property. But I could have easily worked in tangent space notations, which is, for example, what Ashoke does. He prefers to work in tangent space indices.
But whatever you do, you need to have two different metrics, that's the whole.
Yes, that's the crucial point.
That's what's different about this.
Exactly. Because this fields P and Q, that interaction, they have some sort of nice transformation property if the metric was somehow eta, not T. But somehow the linear combination, depending upon this map M, there is a linear combination which has a nice transformation property under the metric G. So there's really two different classes of mathematical objects at play here. So that's why you need these differences. Okay. So this one, notice I could have also simply written the last one as a 9-dimensional Hodge dual with respect to, I mean, this is 9. This is 9 just on gamma. Everyone agrees, right? Because this 10-dimensional epsilon is just going to get rid of this 6 9s and then it's going to put its complement, which is effectively same as the 9-dimensional flat epsilon integral gamma. Okay. And this is with respect to G, this is not 9. So we are dangerous territory now. So this one, given the metric that I have erased, so just to remind you, the metric was G was eta, 9-dimensional eta R squared. You can do one line of computation to convince yourself that this is just this. So you can just write it as 1 over R square star G of, not star, sorry, star 10 of this, and then star 10 of this is essentially star 9 of this. Okay. So we have lambda plus minus some choice. We have uppercase lambda plus some natural choice. And you can easily figure out what is the linear combination of this, right? From here, for example, you can think of gamma I with dx9 as twice lambda plus I plus lambda. And star 9 of gamma I would say is twice of.
But shouldn't it be 9G? 9.
No, because the 9th one I have chosen to be flat. Yeah, I mean, of course, if it was some sort of G in 90, then I would have had that. Yeah, for sure.
So now you're dropping the distinction between the two metrics once they're in 9 dimensions. So you're assuming that you don't have to distinguish.
This remembers that this came from a 10-dimensional metric which had some sort of non-trivial range.
Right.
So once I have, I should also specify that this is the same coordinate in which that metric is expressed.
Right.
That's important, of course. If that form of metric is in some different coordinate system and I'm using a different coordinate system, then of course this might have a different expression. So typically you write the metric in some organized choice of coordinates. And in that choice of coordinates, you can always express the star g, because you see the only thing the star g is going to have the essence in, and then there's the square root g factors which are going to be there. That's the essential difference, and that is how it will remember that there was a 10-dimensional metric with whose star g was important. So in general, if you don't know the explicit form, you would have some sort of some determinant g factor sitting around here, and that you would see that n is a function of that particular guy. But for a given specific metric, you can always do this explicit computations and figure the whole thing. Right? Everyone agrees that I can just replace it, and I will just replace those guys here, and if we can skip a couple of steps because it's straightforward. So this guy is our A, this guy is our S, which gives us M to be negative a half, and the R's cancels. Right? These are all identity matrices, right? S is basically proportional to the identity matrix with this coefficient. A is also identity matrix with this coefficient. So S inverse is all just this inverted identity matrix. The 2R essentially cancels, and then you have R minus 1 by R plus 1, and then identity matrix times identity matrix is identity. So all essentially you are doing is that you're replacing this here, collecting the lambda plus and lambda minus. That's it. There's nothing more than that. And once again, to emphasize, this is basically going to be the same aim for circle compactification in any 4n plus 2. As long as the metric is basically the flat in the remaining directions, and then circle has this R squared thing. So this computation is not going to change. The only thing that changes is that the range of ij's which runs through and stuff like that.
Can you write the M explicitly without breaking Lorentz and Marius in 10 dimensions? I mean, here, of course, you won't break it because you want to read it. But suppose I just want to write the action explicitly in 10 dimensions.
Yeah, if you have a 10-dimensional thing, then you wouldn't have any sort of breaking of Lorentz invariance of any kind, because it's manifestly Lorentz symmetric, this whole thing.
Right, but you couldn't take a choice. Like, I mean, when you took that choice, you singled out one of the coordinates. How would you do it if you did not want to single out? Arbitrary.
I wouldn't single out anything. I would work with the 5 parts and then star into that, and then it's on. Here, of course, singling out it makes sense because of the geometry. But if I don't have anything, then I wouldn't do that.
But you couldn't solve it very easily, changing the star to a star G in small lambda.
I mean, if you don't give me a specific metric, then I will have some square root G factors hanging around, but I will still be able to solve it and give you a name. It will look like some sort of function of square root G's sitting everywhere, and then some metrics.
Yeah. So you're fudging up the star into star G by adding this correct square for G. essentially.
Sorry, can you come again?
So in the first, to work it out,
Uh-huh,
in the first, in the small numbers,
uh-huh.
you have star eta,
Mhm.
but you can fudge it out to star g by adding factors of square root. That's essentially.
Yeah, but I don't want to do that in small lambda. I want to do that in.
Well, to solve for this, the star g on the 5 form now,
Mhm,
or whatever you have,
mhm.
then you want to do it, because then you want it to somehow write it in terms of the.
Yeah, but then the easiest thing to do is that remember that the star g is basically star with some square root g factor sitting around.
Right, so that's what I
So
said.
yeah, that's what I would do here, in here.
Oh, you would go the other way.
Yeah.
You would write this, the star G.
Well, okay, I mean,
step.
I guess you could do the other way also, if you want. Whichever way you do, ultimately you need to find a linear combination of this. Yeah, you could do the other way.
So you would get essentially the same formula, you would get the same with some square root of g's instead of r.
Effectively, instead of
R
r,
is
you have.
essentially square root of.
But then there is something, so the matrices need not be an identity. This fact that this A and A is proportional to identity, it's very particular to this geometry.
Mhm.
So that might not be true anymore. So I should point out that if one is interested in an explicit general formula for M given an arbitrary metric G, then the best thing to use is Ashoke's way of writing it. As I said that in the lecture 2 or 3 weeks before, that there are several ways of constructing M's. All give same answer if you compute on explicit cases. But in general, it is not known. Nobody has proven that the general prescription of this and that is always going to be the same. So Ashoke's formalism has the benefit that it is an explicit formula for M in terms of an arbitrary metric G. So if you have given me some G, and then he writes down some big formula, and then he shows that everything follows, everything, and it has all the properties that it's supposed to have, and blah, blah, blah. This one is more useful for explicit computation. One is that, okay, fine, this is one thing I like about this is that there is a geometric sort of understanding like what this M is doing. It's really related to this matrices S and A, which are basically doing a basis transformation from the cell dual with respect to G and cell dual and cell dual with respect to eta. So in locally it gives you a sort of nice geometric interpretation. And they are very useful for doing a specific coordinate computation. It's much faster than doing it for example, if I wanted to do the same computation in Ashoke's formalism, it would have required me considerable more effort to get the same answer.
But the Lorentz covariance is a little bit obscure in this way of doing it. So.
In this way of doing it, as I said, the Lorentz covariance you can make manifest by simply working with some 5 forms here and there, right? The Lorentz
Yeah,
covariance,
but as soon as you want an explicit expression, you have to pick some basis for the.
yeah, but nothing depends on the explicit expression of M, right? I mean, the abstract definition of this was enough for me to prove everything I wanted to prove.
Yeah.
And the only reason it feels to you that I'm breaking explicit Lorentz covariance is because of this geometry. If you give me a geometry where I don't need to do that, like say, I don't know, 10-dimensional or something, right?
No, I'm saying that if you want to write a more explicit expression for M than that one, you need to pick some basis of 5 forms.
Yes.
And you can't really do that in a Lorentz invariant way.
Say the Lorentz transformation properties are really sort of caring about all these indices.
Yeah, I mean, you can argue in the end, it doesn't depend on how you pick that basis.
Yeah.
As soon as you want a completely explicit one for M, I guess you break ones. So.
No, I don't think that's true. Because what you will have here is that you will have some sort of functional dependence, and then there is something which will carry these IJ indices. The Lorentz transformations are going to hit only those metrics with the IJ indices, and they are going to transform the same way on the both sides. This dependence is something the Lorentz transformations are not going to be sensitive about.
Right.
Because everything here is being done in a way which has manifest local Lorentz symmetry. So when I do a Lorentz transformation, I will do a transformation on this something that might give this ij indices, because this ij are essentially what set of 5 indices, Lorentz indices.
Yeah.
And these indices are what which are going to transform. But this structure is going to be the same on this side. There will be some matrix which will sit here. This matrix might be more ugly looking than delta ij. It might have some sort of thing, but it will be the same sort of matrix which has the same symmetry property of exchange between I and j and so on. So it's the same tensor structure on both sides.
Yeah, okay, and
What is ugly is the general coordinate transformation, because that is this by itself is not going to be general coordinate invariant or have a nice transformation property on logicity.
that's also.
But local Lorentz symmetry, that itself is always sort of guaranteed. That we are not breaking anywhere.
Yeah, as long as you allow your basis to transform, right?
Yeah, as long as okay, I mean, I can always choose a very bad basis which doesn't transform nicely and all that, but
Yeah.
which might be difficult. I mean, you define orthonormality as well on top of being a basis. I think it might just zero in on only the Lorentz invariant ones. If I didn't define orthonormality, I could imagine that I can form some sort of, maybe complicated combinations. Any further questions?
Okay, it's an orthonormality, I think didn't come up before now. Or it was in the previous lecture, but that's also assumed in your basic choice, you assume that it's orthonormal,
This one.
this one.
Yes. So when I proved all these nice properties about N,
Yeah, okay, so it should be an orthonormal basis of that.
yes, yeah, it should be an orthonormal. But small number that into 20. Okay, so once you have the ends, the next step. The next step is to do the mode expansion. I'm going to take this further. And then you need to mode expand the P's and the Q's. So the P is a 4 form, so once again it's going to decompose into a 4 form and a 3 form, which I'm going to call UP and lowercase p. The Q is a 5 form. It's going to decompose into 5 form and a 4 form, which I'm going to call upper Q and lowercase q. And we need to remember that this Q No. Because some like modification. This Q is something which was by definition star of Q, where this star is a 10-dimensional flat star. What this means is that this mode and this mode are no longer independent. Right? So in particular, this means that the nth mode is equal to, and we have negative sign now because it's a 9-dimensional star with Q1. So which means that in this mode expansion, it naively, if you mode expand a 5 form, you get 2 independent set of modes. But then the self-duality essentially tells you that you can get rid of half of them because both of them encode the same degrees of freedom. So it's enough to work with only one. So now we are going to plug in this mode expansions into the action, which I have erased, but I mean all of you know. But in those actions, it is enough to work with either the uppercase Qn or the lowercase Q. And we are going to choose to work with the lowercase Q.
So, what you're saying, all the modes are self-dual.
I wouldn't call it self-dual, but I would say that there's a duality relation, 9-dimensional duality relation, which relates these modes to these modes.
Yeah, but in 10D,
In 10D, the whole object is self-dual.
do the duality mix the modes?
No, it cannot, right?
So the modes are self-dual in 10D.
There are no modes in time.
In 10 there are no modes, right?
It's from expanding the circle.
Yeah.
Using the 10-dimensional star. That's what I mean.
This one is 10-dimensional star, this one is 9-dimensional.
Right, but using the 10-dimensional star.
Yes, this is the
it's-
consequence of.
All the modes are self-dual. Using the 10-dimensional.
There is
All the
no-
coefficients. all
You
the-
couldn't do Fourier expansion in 10D because there's no circle, right?
Yeah.
I don't care. I'm just saying, using the 10-dimensional star, I can do that in 9-dimensional circle. And in that case,
In
the
10
coefficients would be.
in 10-dimensional case,
Yeah.
this whole thing is self-dual to itself. And that tells you that this is good.
So, what is the standard story then? If I have a massless form in high dimensions,
Mhm.
I reduce it, I get one massless lower dimensional, one lower dimensional, one massless,
Mhm.
two lower dimensional, and then the massive guys, I only get one in the standard case because they
So by massive, you mean the higher ones.
the high ones, yeah.
Okay.
So then they have to combine to make up the degrees of freedom of the massive.
No, I mean, this story is like if you have an n form in d dimensions and then you dimensionally reduce, you get an n form in d-1 and then n-1 form in d-1. Right?
Yeah,
Then if
because
the-
you're not doing the field strength. I'm thinking about the.
Yeah, I mean, this is nothing to do with field strength. It's like if you have a differential form. Like, don't think of field strengths or anything, right? Like, for example, here, why did we get a 4 form and a 3 form?
I'm thinking of 1-4. Okay,
Well, okay, one form is a bit special in the sense that here you would get the function in some sense.
I'm just saying that you have one form, you don't think about duality or anything.
Mhm.
You do the dimensional reduction, comes to a reduction, you get a massless one form.
You get a 0 mode and you get an infinite
On
amount.
the infinite tower, but there, they need extra degrees of freedom because they're massive.
Yeah, if they're massive vector fields in lower dimensions, they will have a different degrees of freedom, but the whole Pulsar line reduction tells you that all of this sort of nicely gets captured into a bigger field in this.
Right,
I-
so what I'm saying is that these modes,
Mhm.
for the massive guys, for the higher modes,
Mhm.
combined.
They don't, I mean, I don't know what you mean by combine. Point is that all of this combined to give you this 10-dimensional field, including the 0 mode, not just the higher mode, right?
Sure. So again, go back to photos or one form with two form field strength, dimensional reduced. So to 4 dimensions. So there's a 0 mode, it has 2 degrees of freedom, physical, and then there are higher modes. They are massive vectors, so they have 3 degrees of freedom. So where did the 3rd degree of freedom come from? Well, it's the scalar that you got from wrapping, right? That gives you the 3rd degree of freedom. So I'm looking for something similar going on here. That the massive modes, there will be a different story than the massive modes.
There is a similar story here, right? I mean, this nth mode, naively speaking, would need to have some input from this mode in each level to give you the correct degrees of freedom, such that this whole degrees of freedom and higher dimension is.
So that's, I sort of see how it works. Now, what happens now when the field is self-dual, the field strength is self-dual? So there must be some different things going on there.
Yeah,
because you don't have
exactly. The degrees of freedoms are essentially halved,
right,
in the original ones, and that means that these modes are not really independent. So there is one particular linear combination of them which kind of sort of is set to 0. And then the other one is needed just like for the original case.
So could you just sort of tell me the spectrum, also the massive spectrum? If you take starting 10D, go down to 9D. So what is the spectrum of forms? So I have a massless, 4 form field strength, or a massive 5 form field strength, or
you would get masses for both of this if you don't put any self-duality conditions, right?
for the 0 mode.
No, the 0 mode is fine. 0 mode has no masses.
Right, that's massless. You get for both of them. You get
Essentially we will see what happens to the higher modes, because this by itself, because it's a field strength like object, by itself you cannot just simply say that this will be like masses.
Yeah, it's on the field strength.
Yeah, so it's not really sort of correct to say it's masses. What will happen is that, so essentially, okay, maybe I can just tell you right now. So essentially, what will happen is that for this guys, we will have an interpretation of the masses, right? You will have a massless mode plus a infinite power of massive modes, right?
Yeah.
Because it has a dp with star dp standard kinetic term.
Right.
This one, because of q with dp, it will have massless, let's not call it massless, let's call it 0 mode, plus infinite power of higher modes. These are not massive, these are just some higher modes. Now what happens is that q in itself, remember, doesn't have a kinetic term. Q gets dynamics to dp with q. So what is going to give dynamics to this 0 mode is basically this. Right?
And what about the higher mode?
And all these things are going to get dynamics from these guys.
And after they get dynamics, what kind of dynamics?
It will be exactly the similar set of dynamics, except that now these guys are massive. Okay. But then the point is that the moment I take the shrinking circle limit, all these dynamics are going to get frozen out because these are becoming infinitely massive.
Yeah.
And because their dynamics gets frozen out, their dynamics also gets frozen out.
Sure. But not always do you want to take shrink the circle.
Yeah, if you might not to, then you will get this, or you will have to keep all these infinite towers.
Right. But they become ordinary
This
high form fields, massive high form.
Yeah, this will translate into some sort of massive high form fields, just like the standard case, except that now somehow you're directly dealing with field strength, like objects.
So if you have one form field, somehow it has to provide itself the additional degrees of freedom of the massive guys. Here you get the additional degrees of freedom from the P guy.
not the additional degree of freedom, the dynamics. The degrees of freedom are still in this diagrams.
Yeah, okay.
It's only the degree because remember I showed you that at the level of even the phase space action, this whole thing separates.
Yeah, it's, I'm getting, what's getting a bit confused is if we're doing it from physics, I'm not familiar with.
Yeah, I mean, this is definitely a quite a new feature, right? I mean, this is not a standard way of doing this computation. But here, so remember I showed you that the phase space action nicely separates out into a phase space action of the extra field. I think I call it H field or whatever. Let's call it extra, and then the physical thing.
Okay.
And then as a result, when I do dimensional reductions, these guys are not going to talk to each other. So I can always go to the phase space level and I can always keep track. And there you will see nice and cleanly that this just gives you one massless phase space like thing, and then there will be a massive thing, and then harmless events.
The zero mode is a 4-form field strength.
See, you have a choice. You
Yeah,
can
five
either
or
take a 5 or 4, but because of the cell probability, it's same.
Right. And the massive are also 5 or 4 forms, or
Yeah, exactly, all of them. This is true for all them. This is true for all.
or
all of
there are no oh, yeah.
Which is not that surprising because, I mean, if the 10-dimensional guy is equal to the 9-dimensional guys, whether you work with a 5 or a 4, doesn't matter.
And if it would not have been self-doing,
Yes,
how would this spectrum change? So it has to be doubled somehow.
exactly. This would have its own spectrum, so then the 5 and the 4 are not really the same.
Right.
You can dualize this 5 to get a 4, but then these 4 and that 4 are really different 4 forms. So you essentially get doubling, which is precisely what you should expect.
Yeah.
That's the so okay, so this argument, is it clear that how, because this answers the first essential question that we are dealing with the field strength like variable directly. So there is mode expansion, you cannot really drop the higher modes by saying that these are like mass terms, because you don't have that interpretation anymore. But the way you drop them is because of the fact that what gives dynamics to them, they have an infinite tower of massive modes, and those their dynamics gets frozen out. And as a result, the dynamics of this guys gets frozen out. And that's why the supergravity limit once again get back to 0, which is the correct degree of freedom that you would expect. Right, so this is a sort of crucial trick. And you might ask yourself the question that, not for the supergravity context, but say in general in some other context, if you have a setup where you could ignore the kinetic terms and have some sort of interaction terms involving Qs which start to dominate. This is a sort of standard thing in, for example, in some strongly correlated spin systems, for example, like Hubbard models, where the kinetic terms essentially is very weak and the interaction term is so strong that dominates. In those sort of scenario, you wouldn't have the luxury of dropping all the hardness. And in the paper I give you the reference for, there is a consequence of this, for example, in 2D, if you do a dimensional reduction. This is related to its field theoretic T-duality with respect to a T bar deformed chiral bosons that we found in a different earlier paper. So in those kind of scenarios, this sort of plays an important role, this sort of fact that you cannot really discard them, thinking of them as infinite masses. But for supergravity, of course, the kinetic terms are important, and then this is what helps you.
I have a question.
Yeah.
This will be at the equation of motion level, right?
Which one?
Using the fact that the infinite number of master modes for P will freeze out the higher modes for Q.
No, I mean, even at the action level, you will have actions like BPM, star line, BPM, but then you will have something like N squared, well, L squared, PN squared.
Okay.
And then the moment I take the limit of the circle, physical size of the circle shrinking to 0, all of this becomes infinitely massive, right? So in the path integral, this really sort of, all these modes sort of drops out.
No, I was asking about using that for Q.
Exactly, because the PNs would drop, then you would have a term here which would be like DPM which QL.
Oh, right.
So then the only way that this would have a sort of kinetic term is through this line. If its dynamics drops out, then there is no way that will sort of play out.
Okay.
No. All the time.
Well, okay, I will just continue. Okay, so yeah, now there are sort of a bunch of essentially standard calculations. So let me just give you the sort of outline. So first and foremost, you need to replace this mode expansions under action that I sometimes that I erase it, and just focus on the 0 modes for this reason, right? And it also turns out that it helps if you rescale this PL to L times PL and small q. Remember, we don't work with uppercase q, we chose to work with only the lowercase q's. L by 2 QL. And then if you do that, just the 0 mode action looks like so these are all 0 modes, so there are no substitutes that's right. So the only thing that is being done is that you take the 0 modes, plug it back, work only with the small q's, not with the uppercase q's. And then in terms of that, you have this. So these are the ones that comes from the DP weight star DP intensity. Now there's an item for the curly p and the lowercase p. And these are the ones that comes from the q which DP, right? Because you chose to work with this small q's and not capital Q, that's why one of them has a star line and the other one doesn't, right? And then this is the q by q term. You will notice the in factor coming out nicely, and this 2 over L square is simply because we chose to rescale these q's. These rescalings are simply because you know that towards the end I want this to look like type 2A, and that's why. At this point you don't have to do these things, but then towards the end we write down a big field definition, so it's easier to do it step by step in the intermediate steps. So if you are really doing an honest computation, in my opinion, this is where you should just stop. Because that's what you do in type 2A, right? You have the action, mode expand, plug it in, keep the 0 mode, see what you get. And that's what all we have done so far, except for this rescaling, forget about that, but that's all we have done so far. But this is not enough simply because of the fact of this point B. We need to somehow make connection to a formulation of type 2A, which is done in potential, not in terms of field strength. And as I keep on saying that string theory tells you that you really should formulate all of the supergravities in a way such that all the Raman field strengths are expressed in this way, through field strengths, not potentially. If somebody had formulated type 2A supergravity in that language, then I would argue that this is where you should stop. Because the type 2A also in dimensional reduction would look something like this, and you can easily compare. Because it's also this point B doesn't exist. That is also in the field strength based formulation, and you just compare. But since it is not, we have to do a bit of extra work to reduce it to this form. Okay. And so this extra work is not something that is very difficult. It's once again standard technology that people have been doing in supergravity literature for a very long time. The first thing is that we need to sort of pointer dualize one of these P's. So instead of P in favor of this P, we want to trade in a C, which will be a P form. So let me write it as a C3. Apparently, this C3 has nothing to do with the Raman potential, and just some variable, some P form. Okay. And the way you do that is that in this 90 action, you add a total derivative. Which is this. Which is something I can always do, right? In other words, what I'm doing is that I'm pointer dualizing this curly P. That's all I'm doing. And that's how you do it, right? You introduce a total derivative. And then step 2 is you integrate out curly P. And instead of this action now having instead of curly P dependence, it will start having C3 dependence. Right? Everything is quadratic in curly P. This definitely doesn't change that fact. So you can integrate out curly P and you get an action which will now be a function of C3 small p small q's, and that's it. In other words, I'm just simply dualizing this curly. It's a simple statement, and if you want the action, if you just do this two operation, it looks like this. So this is the resulting action. Just after these two steps. And a total derivative, I integrate out curly P in favor of C3.
So. I'm confused. Integrate out means using equations of motion.
Yeah, you can use that is one way of doing that. Or you can complete the squares and take
Yeah,
out
but then-
one linear combination now.
But since that term is a total derivative, how do you get anything from?
Yeah, you'd have to use the boundary term.
Yeah,
Yeah.
No, this is total derivative, so it definitely doesn't change anything of the dynamics, right? The equations of motions are the same.
sure.
So
So it means, how can you use the equations of motion of P to integrate it out?
yeah, then I will have, after this, I drop the boundary term. I find the boundary term. Then if I vary with respect to sort of, okay, essentially the point is that every time you add a boundary term like this, you basically, I don't think using the equation of motion is the correct way. I think that essentially the point is that you complete the squares. And then you sort of, so there will be a piece which will be some sort of linear combinations of P and C, which will completely decouple. And then there will be a piece which is only in terms of C's, which is what it will remain.
And C and Q.
The Q's are, I'm not doing anything to the Q's and the lowercase q. It's only the upper curly P.
Yeah, but you have a term which mixes C and Q. Also.
Of course, because there is a term which is curly P with Q. This term.
Mhm.
So when I complete the squares, right, there will be a contribution that comes from this thing.
You have to show me. Complete the square, please. I'm just being stupid.
I mean,
We're adding something to dp, I guess.
yeah, it's just simply saying that. So essentially what you have something like, dp squared, then you have dp with something, and then on that something you have added something like a dc, right? So what you do is that you define the dp plus all this somethings together to be your new dp data. And then essentially you add and subtract dc squared in such a way, not just dc squared, but also this something squared. That the first term becomes dpt plus squared, and then you have all these guys remaining, dc squared and something squared. And then this dp tilde is something that completely factors out.
Yeah, on this level,
But this is really nothing more than that. I mean,
I don't really see how it can work. The square term that you're adding things to has a star.
yeah, that doesn't change anything, right?
So you're adding, let's say, DC terms to DP, right? So you're gonna have something with one thing with a star in it, and how do you get rid of the star to get the
You don't
last
need to
term?
get rid of the stars, right? This is the thing which gives you the perfect square. dp with star dp.
Right, but how what I don't understand is the total derivative. It doesn't make sense to me.
The total derivative, what doesn't make sense?
How can it change everything?
It doesn't change anything by its own. You have to integrate out the p as well. And then
Right, but that's, integrating out the is equivalent to completing the squares.
it is equivalent to the completing of the squares. That's what I'm saying.
So,
That
but then how can the total derivative give anything at all?
okay, this is too big an example to do that, but let's look at the simpler thing.
I mean, it's not so big. There are like, what? 3 terms. We should be able to do it.
I did do it, that's how the paper.
I understand, but this is for my benefit.
But I mean, also the point is that this is not a non-trivial use step, this is really a textbook step. Of any programming.
That's why it's so frustrating.
Yes. So let's say you have something like this. So these symbols don't mean anything right now. These are just something new to learn. Okay.
Okay.
And then I'm adding to it something like this. All I'm saying here is that, in fact, let me not worry about how also.
Okay.
All I'm saying is that let us define BP plus Q plus DC.
Okay.
And maybe I want, let's see what this gives.
Yeah.
And let's call it dp tilde.
Right.
And then let's do dp tilde which
Right.
star dp tilde. So I get dp which star dp. I get dp which q, but then I get star dp which q, which I can make it.
Wait. DP, well, because Q is self-door.
Yeah.
Yeah. Okay.
But first of all, it's not really D of something, right? Because Q is not.
No, I can define a dp tilde like this.
Why?
Why not?
Why?
No, but why not? I can.
Because it's not.
That's exact, but Q is not exact.
So that's the second problem, but just do this calculation.
But I'm doing a field redefinition at this point, let's say.
Yeah, but so should we make sense of the DP of adjusting DP?
So call it Q tilde or whatever, right?
Yeah, okay, that I can do that as well.
This is just a shorthand for.
Yeah,
for-
Sure. It's just a start.
Yeah.
Okay. Now, so I agree. Yeah, these two terms I agree with.
Yeah, then I have DP which DC.
So where did the star go?
No, I'm writing it. I will have a DP which star DC as well.
So where did you?
And what other terms are there? Q with C.
No, I don't know. I don't see where this second to last term comes from. DPDC. Where did that come from?
Oh, maybe not, right? Yeah, it would be star DP with.
Yeah.
Oh, so then let's do it.
Now I'm happy.
Right.
Then I'm more happy.
And then what do I have left? I have Q's with C's, right? So I will have Q with star DC. And star Q with DC, which is exactly the same as this. Which means that this thing, I can now write it as Q tilde with star Q tilde. And then I subtract off the extra piece that I don't have in this expansion, which is this guy.
Wait. So I'm going to star.
And I will also have a C with C, right? There will be a C with star with C.
I have a question, but if you have the half from the factors from our match,
Which one?
if you have a half DP's with star DP.
Yeah, then here I change some of the numerical coefficients, right? I want this guy to be half, and then I change the numerical coefficient. The point is that there is always some linear combination with which I can complete the square. Look, this is just simply, I don't know why this is so complicated. This is simply saying that it's p squared plus p times something. It's basically a quadratic, right? It's p squared plus p times. I'm just simply saying that you can always find q tilde equals to p plus some object k, such that you can write this thing as q tilde squared plus k times q tilde and so on.
Yeah.
Not q tilde, but k squared plus.
You know why it's confusing? Because you started by saying, if I have this term, then I can complete this.
No, I said if you add this term and then integrate out P. I never said that if you add this term, then I can do this thing. I said two of the steps and both of the steps are needed. And then you
No,
get
but
this.
why do you need to add this term? Because now you show that you can write this as a square before doing anything.
No, I had to add this thing, right? This cross term.
It's zero.
It's not zero. How?
It's boundary.
It's a boundary term,
It
but
doesn't contribute to integrating out.
no, but I mean, I could put it in a non-trivial boundary.
Do you have a non-trivial boundary?
I could. This is at the level of action. I have not
If you had
specified.
started by saying, okay, well, we'll be careful around non-trivial boundary, that's not something that I would assume like at the first.
I mean, this term adding or subtracting this term is not controversial, right?
Depends how you say it. Right? If you say it like it's necessary for having something,
I did not say it's necessary. I said that
well, that's the way I understood it. Okay, I'm not saying
to
you said
this action,
right?
starting from this line
Right.
to go to this line. I'm just simply saying that one way of doing that is that you think of adding a total derivative and then you integrate out. If you don't like that, you can say that arbitrarily I can do a field redefinition where P is some linear combinations of PC3 plus PU plus something. And then in terms of that new field redefinition, this new P tilde decouples, and then in terms of the CPs and etc., I get this. And then that decoupled thing works out. Both are equivalency. Right? Because it's at the level of quadratic theory, it's a Gaussian path integral.
The way you order things made me think that the whole thing is a consequence of this term. The thing that's integrating out the P is a consequence of having that term, which it is not. You can do it without this term. If you don't have a boundary.
It's exactly the same thing. It's exactly the same thing. I would generate a boundary term there as well, in doing the field definition, and then I would throw it.
So I'm just trying to explain why I was confused.
Yeah, I mean that's perfectly fine, but at the same time, this is something which is sort of very standard. I mean, there's nothing non-trivial going on here. It just there are more fields and it has some forms and everything, right? Okay. So now, if you're convinced that pointed dual works, is it okay if I use these things? No. I mean, just the auxiliary parts, not the main case. Okay. So then the next step is to do a further field redefinition and define what we are calling C tilde, which is this particular linear combination. And this field redefinition is chosen simply so that this whole thing can be recast into something that looks like what you would get from type 2. There is no other motivation. If I didn't know how type 2 thing looks like, this thing would have been very artificial. Like, in fact, even this would have been very artificial. As I said, that we should really stop here. But we know that there is a way, there's a form of action we want to bring in. That's why you do this. And then if you do that, this action becomes essentially you have two four-dimensional field strength in potential formulation, but one with a wrong kinetic term, another with the correct kinetic term. In our sign convention, having the minus sign is the correct kinetic term. Which is, of course, as it should be, because the extra field in sense formalism is never going to go away. When you do dimensional reduction, the extra field is also going to get dimensional reduction, and there's always going to be an extra piece. So this is not something that you would ever see starting from the type 2A in the potential formulation. This is the one that you see from the type 2A potential. And so this is the identification. So this is the, so you can use the color.
So you're not really finding C, you're really finding small p. But you're replacing.
No, there's a particular linear combination of small p and C.
Yeah, but
Which is
Yeah, but in your action, you're keeping C.
yeah.
So instead of
Yeah.
small p, you're putting
Yeah,
C
yeah.
and C.
So this you identify as the extra physical right. And this is the one that matches 2A. Of course, 2A is simple dimensional reduction. Except for one small subtlety that I would like to point out is that remember the physical size of the extra dimension, the perimeter was R times L in my way of parameterizing this thing. The circle had perimeter small r, dimension this number times L, right? So you see that
is R less than 1?
the R is the one which you take the limit to 0 in the shrinking circuit level.
Is R
So R you take to 0, but this one you want to keep, so you remember like this acts like a sort of coupling.
So you say that the fact action just stupid for convention. So your actions are negative different?
This one is negative. So in my Lorentz sign convention, the standard thing would be
where the ones. Okay, yeah.
it's negative DC, you have to start DC, which is the correct kinetic term.
Okay.
So in type 2A, you would start off with the Lagrangian, which is negative DC P wedge star DC field. That's the correct. This is the positive definite I'm looking at. So that's why I said this one is the unphysical one. Okay, so what I was going to point out is that you see that if you start off from a d-dimensional action, you do kk reduction to a d minus 1, then typically this one has the size of the circle in the numerator and then some d minus 1 Lagrangian. Simply because the volume form here in the dimensional reduction factors out like RL times the volume form in the 9 dimensions, so it should be in the numerator. But here you see that it's in the denominator, which is quite weird. We did a standard coupling and we followed the same philosophy. That is because of the non-standard coupling, this comes up. Now this doesn't mean anything in the free theory because I can once again rescale C tildes and just get rid of this. And this is the correct thing to do in type 2. That you cannot, sorry, in type 2. That you cannot see just from this level. But remember the full action also has this Chern-Simons stance, for example. If you had kept track of that, then you see that you don't need to just match this, but you also need to match the dimensional reduced version of the type, the Chern-Simons one. And then you see that the correct answer would have been the one, which is you rescale this C tilde to be RL times C tilde.
But the 2A is compactified on a circle of radius 1 over R.
Yeah, so you could say that this is somehow directly giving the type 2 answer, which it should not, right? Because this is the type 2B computation. So whichever one way you want to look at it, there is a bit of a puzzle. But this thing for the type 2B, this is if you really want to sort of give it rise to the type 2B thing, you just rescale by this and then everything matches. But the fact that this came out to be 1 over RL is actually a good thing when you think of applications of circular formulas in other dimensions. Especially, I want to emphasize this thing, So if you have 2, 0 theory on 60, and if you do dimensional reduction of this on S1, this is known to give rise to a finite superior mills. So you would expect some sort of, this is a 5-dimensional monster, something like this. Of course, there will be some other terms, but with the leading order, you would expect something like this to come out, right? And the whole question is that what should be the factor of the, so this is dimensional reduction on some circle of radius, say R. Okay, so what should be the factor of R sitting in front? Should it be in the numerator or the denominator? That's the question. And then, as far as I'm aware, Witten gave a very nice argument in this paper, and as far as I'm aware, this is the first time that such an argument was spelled out, but maybe it was known in the community earlier. The simplest way to fix this is by remembering that this theory is conformal invariant in 60. So if you take the 6-dimensional metric and you rescale it by some positive number, so let's say some alpha squared G60, so alpha is some real number, right? So if you rescale the 60 metric, there is some metric here, right? And it's dimensional reducing of S1 times R. Then this 5-dimensional monster, this scales as alpha times this. And the radius R, that should also scale alpha times this. Which means if this guy is supposed to come down from a scale invariant theory, then the R should sit in the denominator. And there is some number that can be here. We are just doing a dimensional analysis at this point. And this Witten pointed out in this paper that this is a very strange feature because it suggests that this dimensional reduction cannot be the standard Carnot line reduction. Because if you do that, you always get R in the numerator.
Does this like appear in all like a reduction of conformal field theory to like S1?
No, this is very particular to 2, 0 theory. There is a big brother version of this where you take 2, 0 theory on torus. So say torus is 2 circles of radius R1 times R2, right? Standard Carnot line would take, and this one is supposed to give you electromagnetic kind of theory in 4D, but it would have S duality. So standard Carnot line would tell you that, you know, the action should be R1, R2 times some L4. Because you're doing a dimensional reduction on 2 by R1 times 2 by R2, and the volume factor is R1 times R2. But then this one will not be S duality invariant. For this to be S duality invariant, it has to be some function of R1 over R2 or R2 over R1, whichever way we want to look at it. And this is, once again, if you do reduction of sense action on torus, this is the kind of factors that comes out very naturally. So this was first pointed out, I think, in a paper by Neil Lambert, but also Ashok pointed out in his 2019 version. That, of course, this by itself doesn't solve every puzzle regarding 2, 0 theory. But it's one direction in which it is providing a strong input. That having a non-standard coupling to gravity through, because it's not coupled to the gravity in the standard way. You just don't replace eta by g and the volume factor by square root g times volume factor, etc. You couple to the gravity through this weird map M. And that is somehow very crucial in sort of getting these strange factors that could be otherwise argued indirectly based on S duality or conformal invariance in gravity and so on. So I just wanted to point out this fact that this is a sort of Like while at first it might seem a very strange idea to couple this gravity in this non-centered way, it's actually helping you to understand some of the puzzles which have, confounded the community for decades. In fact, this is touted as one of the reasons that why this cannot have an action. Like if you have an action, then you could, people say that if you had an action and if you do a dimensional induction, you should get hardened and be melted, but you don't, so you cannot have an action. One of the reasons. So that reason at least has gone away. But of course, there are other objections which this formalism by itself doesn't negate, right? Okay, so I think in 10-dimensional T-duality, that's all I wanted to say. In our paper, we also discuss use of this formulation for T-duality on the Walshing perspective. So that's a 2D, and then of course there is this field theoretic T-duality, which I very briefly mentioned, which is connected to certain integrable deformation of quantum mechanics with the Hitchcock deformations of the chiral bosons in sense formulation. But I don't want to discuss that. Instead, what I had in mind was discussing another one of my paper, but I didn't assume that this one will take 2 hours. So this is actually a natural point to stop. Unless you want to sit in 2 more hours.
How do you feel about next week? This is the last. Okay, what does the organizers feel about next week?
He's busy next week.
Yeah, next week I'm unfortunately not.
That's it. So it's heavily.
Still a long time till Christmas, no?
I mean, if people are willing to come and listen, I'm willing to stand here and speak.
Sure. So in 2 weeks would be possible.
Yeah, unless you already showed that.
No.
So there is some there that.
Cloud was invited a speaker, but I think February first week is. Yeah, I mean, beyond that, he's not available for December, so.
Yeah.
Next semester, you mentioned that Hassan might be there for last week of January, so first week of February, that's fine.
But there was some day in December, this room is occupied.
December. I mean, next week is 28th, so that is fine.
The
5th
week
is not-
after that, no. Okay, but should we thank the speaker?